When you think about crystals, what often comes to mind is that striking visual appeal, right? Their perfect symmetry, those polished surfaces, they just look so, well, ideal. But here's where it gets really interesting. Beneath that shiny exterior, there's often a far more complex, even challenging internal structure. So today we're doing a deep dive into exactly that, into those hidden complexities. Specifically, the surprising world of crystal imperfections, thanks to some truly groundbreaking new research.
Yeah, and what's fascinating really is that these imperfections, they're not just minor flaws at all. I mean, they might seem like tiny structural mistakes, maybe a missing atom here, an extra bond there, but they can have these really profound mechanical effects on a material. Sometimes they can be the start of a fracture, but remarkably, sometimes they actually improve the material's strength.
Improve it.
Yeah, and that's a really crucial distinction, the actual mechanical impact these tiny deviations can have. So understanding them isn't just some academic thing. It's critical, a critical area for scientists, for engineers, anyone looking to design the next generation of materials.
Exactly. And the really exciting part here is the specific breakthrough we're talking about, led by researchers at the University of Osaka. They developed these new mathematical models. It was published in Royal Society Open Science, and they offer this fresh, really rigorous perspective on how crystals behave, especially, when these so-called flaws are present. It's genuinely transforming how we look at what's going on inside.
Which, raises a big question. How do you even start to mathematically describe something that isn't perfect? Traditionally, it's been incredibly difficult capturing the nuances of these structural flaws with mathematical precision. Really hard. The lead author of this study, Shinsuke Kobayashi, points out that defects come in, many forms. For instance, you've got things called dislocations. Think of those as being linked to breaking translational symmetry in the crystal.
Okay, like a row of atoms that's just misplaced.
Exactly, like a slip or a misplaced row. And then you also have disclinations. These are more about breaking rotational symmetry, like if a part of the crystal lattice is twisted or bent somehow.
Right. And trying to capture all of these different kinds, these dislocations and disclinations with their, distinct geometric properties, trying to get that into a single mathematical theory hasn't been easy historically.
None at all.
Previous models, in fact, they really struggled to reconcile the differences between them, right?
Yeah.
Highlighting that, something needed changing in the theories. So given those challenges, especially telling those two types apart mathematically, what was the specific insight? What was the new approach the Osaka team used to finally break through that barrier?
It was differential geometry. Yeah, imagine a branch of math that's specifically designed to describe curves and surfaces and spaces, particularly when they're bent or twisted or, irregularly shaped. Ryuichi Terumi, who's the senior author, explains that this framework gives you a very elegant way to describe these really rich phenomena inside crystals, especially when they deviate from that perfect symmetry. And this is where the real power of the mathematics comes through. Simple mathematical operations within this framework can capture these effects. It let them focus on the similarities between defects that previously seemed, totally separate.
So how do they actually apply this, complex-sounding geometry to crystal structures? It sounds incredibly difficult, like trying to map the inside of a tangled ball of yarn with a microscope.
It is sophisticated, yeah. They used a mathematical framework called Riemann-Cartan manifolds. Think of it as a kind of specialized geometry. It's for describing spaces that are curved or twisted in very particular ways. And this mathematical space turned out to be the perfect tool. It let them rigorously model the internal distortions within crystals. And that allowed them to finally prove this deep underlying relationship between dislocations and disclinations.
Wow.
So, for instance, they could mathematically represent a disclination that twisted part not as some separate issue, but as a specific type of curvature within this new geometric model. And that revealed its inherent, precise link to dislocations. Before this, scientists mostly just had, empirical observations of this link. The rigorous math behind it was a bit of a mystery.
So it's almost like they found the universal language, the math that connects these different types of imperfections. But this isn't just about theoretical elegance, is it? Finding that language also let them derive precise analytical expressions for the stress fields caused by these defects. And that has some very real-world implications, doesn't it?
Oh, absolutely. It really does. If we connect this back to the bigger picture, this whole geometric approach to describing the mechanics of crystals, it could eventually inspire scientists and engineers to, design materials with very specific, tailored properties.
Right. like custom materials.
Exactly. Imagine being able to intentionally introduce and control defects, not to weaken the material, but actually to strengthen it. We already see hints of this, like how disclinations can sometimes improve material strength.
That's a truly mind-bending idea, isn't it? Intentionally breaking something, introducing a flaw to make the whole thing stronger.
It really is. And this research, it's not just about understanding the materials we already have. It's potentially a roadmap for creating entirely new ones. I mean, what if we could routinely engineer materials, give them enhanced strength, or maybe other desired qualities, just by intelligently harnessing what we used to just call flaws?
That really feels like the core aha moment here, doesn't it? How this abstract mathematical rigor, this geometry, doesn't just explain why crystals sometimes break, but actually gives us a precise roadmap to engineer their internal flaws, turning potential weaknesses into, well, incredible strengths. It's transforming our fundamental understanding of materials, quite literally, from the inside out.
That's it. This geometric understanding offers that roadmap, a way to harness those flaws for potentially incredible advantage. It really highlights how understanding something at its most fundamental level, its mathematical level, can unlock completely new ways to interact with and maybe even design our physical world.
That's truly the incredible potential here, transforming what we once just saw as weaknesses into levers for, unprecedented material strength and design possibilities. It's a real testament, isn't it, to how deep mathematical understanding can literally reshape our physical world, turning these theoretical breakthroughs into tangible advancements down the line. What a fascinating deep dive today.